This is the part 2 video podcast for the lecture on flood hydrology. And what I want to do here is I want to introduce you to the concept of the natural flow regime, define the elements of the natural flow regime, and then give a number of examples of specific analyses that you can do. And these are kind of your breadwinner, moneymaker analyses that as a hydrologist you can just do and really characterize the natural flow regime for a client, and understand what the processes are that are at work in a system. The natural flow regime is an idea that has been expressed in a series of papers, but began with Poff et al. In 1997. Probably had precursors before that, but that's really the one that's been cited the most. And the main thing is to just recognize that discharge, when you're looking at a river, so not as much in an uplands context, but once you have perennial flow, or potentially even in an ephemeral, infrequent flows, ephemeral flows, but essentially a channel-centric perspective where you're looking at what is the discharge that's coming out of that watershed and analyzing the time series itself to get what you might call a signature or a style for what the regime is like. Regime just means that all the characteristics that are going into it, natural just indicating that in an unimpaired, no human activities. But certainly there are going to be natural disturbances, and disturbance, whether they're droughts, or floods, are diagnostic indicators of aspects of a natural flow regime. And so there's a lot of elements of ecology that are tied to specific markers that occur throughout the year. So that leads to these components being the magnitude of flow, the frequency with which different flows occur, seasonal timing, flow predictability, duration, and then rate of change of flow conditions. So we're going to work through these, but this is just another way of illustrating the natural flow regime. On the x-axis is time at 3 different spatial scales: interannual, annual, and seasonal or monthly scales. And so, here's a time series. Like, let's just say the y-axis here is discharge. It's on a log plot of some kind. And so you can see that there's a lot of variability, both daily, seasonal, interannual variability, and embedded in that is some sense of the predictability of that. If you see something like tides that are just oscillating according to a sine function, that's highly predictable. We can also look and say, okay, well, here are floods that are occurring in a particular year. What is the frequency with which those magnitudes are recurring? Maybe there's a low flow period, so what's the duration of drought? So duration, seasonal timing, what are the floods? And then you could just look at, for an individual hydrograph, like the magnitude of that, as we've looked at before, and the rate at which water rises or falls. That's what we call the rising limb or falling limb. So I'm going to work through these, and the first most basic thing is flow magnitude. Now, important thing to understand about using the natural flow regime as an idea to guide your analyses, there's no predetermined factor that's like the end-all be-all. And flow magnitude, just like any others, falls into this. So flow magnitude is any metric that tells you about the amount of water moving past a fixed location per unit time. So it's going to be a discharge measurement, but it could be like cubic feet per second, which is more or less the instantaneous flow. However, it could be, the water year total amount of flow or other storage indicators. So here's some specific example metrics. Mean daily discharge is typically the raw data that we get from, a gauging station. I shouldn't say raw, but it's the product of a gauging station. Mean annual flow, so like the total amount of water volumetrically, which could be in cubic meters per year, or in the United States we often see acre feet per year. You might take the peak flow, being the largest event that occurs in a 12-month period. And so this graph just shows a time series of discharge for a river known as Western Run in Maryland. It shows the mean daily discharge on the y-axis, and you can see that from 1944 to 1994, like a 50-year period, there's one event here in 1972, probably Hurricane Agnes, that's like the biggest event on record. But there are also a lot of other peaks, and then there are base flow, snowmelt periods, and lots of things. So you can pick anything depending on what assessment you want to look at. If you're building a bridge for civil engineering, maybe there's some specific thing that matters. If you're looking at a particular organism in a particular time of year, maybe it's something else. Flow timing is the next metric. This relates to the dates during the year that flows of interest occur, often derived from long-term records. Typically, this flow timing has a lot to do with whether runoff is due to rainfall or snow or snowmelt or something else. So, for example, here's a graph from a book that shows 3 different rivers: the Smith, Cosumnes, and San Joaquin. The Smith River is one where it has a lot of flow throughout the winter and into the spring. Whereas the San Joaquin is a river that has very low flows in the winter and very high flows in the spring. So a snowmelt-dominated regime versus rain-dominated. And the Cosumnes is a blend of those two end members. Now this is looking at flow over 1 year and seeing on average for multiple years, like what is the average condition in November, December, and January, and so on, like the monthly average state of the system. However, flow timing can be at any time scale. There's, again, a wide variety of metrics one could use. And that's one of the challenges with the natural flow regime as an approach is that, there are things that people have commonly used, but they aren't necessarily the right or wrong ones for the problem you're working on. So you really have to think about it and decide for yourself what you need. And here's a list of some specific examples that you can read through on your own. This is a really cool kind of diagram. Like if you take all of your data for flow, like let's say you have a discharge record from 1904 to 1994, so 90 years of data. If you take the data from each year, you have 365 or so points for daily discharge, and you put it in a column, then you can make a plot that shows for, all the data over all of the years. So each one of these plots, the years are increasing, let's see, from left to right, so it's increasing time that way. And then the day 1 is January 1st, 365, December 31st. And it's plotting the totality of all of the data that you have on record as a three-dimensional plot. So this is something that you could do with you can't do this like in Excel, but this is something that you can do with a lot of other kinds of software. And what you can see here are different signatures of the timing of flows. So the first one in the upper left, fairly moderate flows with high base flows and not so high peaks, whereas this next event has wide variation to flows. We could think of that as fairly random with not a lot of predictability there. Here's a case where there's seasonal snowmelt. So a very strong peak here during the spring, maybe some small flows during the winter associated with rains. And then here's an example where there's a fairly steady period with some very large spikes. That's a rainy season, and then a low flow period that's a dry season. So, rather than just looking at all the data as a single two-dimensional plot like you see here, you can see how comparing this plot to one of these, you get a very richer perspective on what's happening. And then if you pile on top of that, not just a natural flow regime, but an altered one, you can see something here. So we're seeing throughout the year from 1930 forward and then 1940, so throughout the year, and this is organized by water years. And so in the United States, the water year begins on October 1. So you can see this very dry periods that are present, very dry, and then very wet periods. So you see like this, it's essentially a wet season, dry season scenario, but then the wet season isn't so much snowmelt dominated, but with a lot of variation in its events. However, then a dam gets built here in the 60s, and after that, the lows are not as low and the highs are not as high. So a dramatic change in the natural flow regime as a result of the damming that was done. Another variable for the natural flow regime is flow duration, which is the period of time associated with a particular flow event. The flow duration, you've already used that in the wetland assignments that I gave. So you could use it to say, well, how much of the time does flow exceed or not exceed a certain level? So for example, if we come to a depth of like 1.3, that's exceeded 10% of the time. We could define a truncation level, like if you're interested in droughts, anything below that would be a drought, or if you're interested in floods, you can pick a level and say anything above that you could define, and then see, well, what is the duration that you have flows above or below that, or maybe the number of, well, that's just duration, yep. This is something that we've been through several times without really looking at it quantitatively, but in terms of flow frequency, that's the number of times an event of a certain magnitude recurs. And so if we say something like a 100-year event, like I talked about a lot during the urban consequences presentation, you can take a 100-year event and then we can convert that by saying 1 over the recurrence interval, 1 over 100, which equals 0.01, and 0.01 is 1/100th, which means 1%. So a 100-year event, that discharge level or magnitude is exceeded 1% of the time. So if we want to get non-exceedance, we say 100% minus 1 equals 99%. So 99% of the time, this is not exceeded. And you could do this for anything. So if we say a 2-year event, you just take the 2, 1 over 2 converts it to the frequency, and 0.5 is 50% of the time, and that's the same as an exceedance or non-exceedance. So there are procedures for calculating flow frequencies. It's not something that we're going to do specifically in this class, but you may do that in another physical hydrology or stochastic hydrology class. Here's an example of a flood frequency analysis plotted on normal probability paper. So I think I've mentioned this before. This is a plot in which data that falls along a straight line is fit to a normal distribution. If you in this case, because the y-axis is on a logarithmic scale, then if it fits on a line like you see here, then it's pretty much fitting a log normal distribution. But in general, what you do is you take your data and you sort it from the smallest event to the largest event. And when I say rank, you say, yeah, rank 1, 2, 3, 4, 5 from largest to smallest. Then there are formulas that can calculate the non-exceedance probability on the basis of the ranking. And that's where it's not something that we're going to do in this class, but if you're interested in that, that's commonly covered in a variety of hydrology textbooks. And then Excel does not have probability paper. This plot was made using Kaleidograph. And Kaleidograph, you don't even have to do the analysis. The analysis is just done natively in Kaleidograph. Excel can do the analysis, but it just can't make this kind of plot. Flow predictability. This is really important. I mean, just like any other time series, we often want to be able to predict what's going to happen in the future, or just understand for past events, might we have predicted them? When you're talking about a time series, a key measure of predictability is if data can predict itself. Like, does some event that takes place foreshadow the next thing that's going to happen? And when we look at that kind of foreshadowing, we have a metric called autocorrelation. You know what correlation is? It's like you take one variable and you put it in one column in Excel, you put another one in another column, and you say equals coral, and you put the two arrays and you get a number. Well, autocorrelation is when you correlate it with itself. Now, how does that work? Well, if you could pause here, go get yourself a little piece of paper and a pencil. So pause and paper and pencil. Okay, now you have paper and pencil. Write down in a column 1, 2, 3, 4, 5. Then in the column to the right, next to the 2, put a 1. Next to the 3, put a 2. Next to the 4, put a 3. And next to the 5, put a 4. So what you can see is I have essentially shifted the numbers down 1. There's no number next to 1, and there's really no number. There's the second column has no 5. If you went to another column, you could shift it one more and shift it down. So you're taking a column and you're putting the next column. You're just, instead of having it next to itself, which would have a autocorrelation perfect, you're just shifting it down one. You could also then, the lag is the number of cells that you're leaving blank. So instead of shifting it 1, you could shift it 2 or 3 or more. And that's the number of lag. So what this plot shows here is if I take a time series, that western run data that I showed you before, and I lag it 1 day, 2 day, 3 day, and so on, like just shifting it 1 cell, 2 cell, 3 cell, because it's daily data, then I can calculate the autocorrelation, which is basically the correlation between the data and itself, shifting it so many days. And of course, it starts off a very high correlation, but even by the time you get to just a few days, there's very low predictability. I mean, even to get down to 0.03, that's 146 days. But very quickly after even like 5 to 10 days, the flow is no longer predictable. So like knowing the flow today, I can pretty well guess what's going to happen tomorrow and the next day, but what's going to happen 10, 20 days out? Well, to answer that question is telling you something important about the river, and that's why flow predictability is a useful metric of the natural flow regime. Another thing you can do for predictability is just ask yourself an even more fundamental question. Is the data you're looking at random or patterned? And when you have a time series, there's a very simple test to do, although of course it's new to you, so it won't feel very simple to start off with. It's called the U-test for runs above and below the median. So imagine you have a median, so I'll just cut myself in half here. Anytime you're above that, you're above the median, and if you're below it, you're below. So if you spend a lot of time above, and then you drop, and then you're below, and then you come up, you can start to look like a tidal wave, right? So a tidal wave is highly predictable, and it's going to have consistent times above the median, and then a period of time below that, and it's going to flip-flop back and forth. However, if it's random data, it's just going to be boop, 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 all over the place. It's not going to be consistently yielding runs. Like a run is when you flip a coin and you get the same result over and over and over again. To be above or below the median, it's kind of like flipping a coin. You're either above or you're below. So I've listed the steps. I don't think I'm going to talk all the way through them, but I've given you the general idea. You basically need to figure out how many runs there are. So like, am I here in this parenthetical, 1 means I'm above the median and 0 means I'm below the median. And I just count the number of times that happens. So in this case, 1, 1, that's a run. 0, 0, that's a run. 1 by itself is a run, 0 by itself, and then 1, 1, 1. So there's 5 runs. Now, if I were to just flip a coin as either a 0 or 1, what are the chances that I'm going to end up with 5 runs, like of heads and tails? And the answer of that is what we call the expectation. The expectation is the number of runs you would have if the process you were doing was random. And I'm not, there are the formulas to calculate that, and you'll have that as a homework assignment, so you'll be doing that. Once you have the number of runs, you calculate the mean and the standard deviation, and then you take your observed value, which is R, that's your number of runs R, you subtract the expectation, divide by the standard deviation, and that gives you a standard normal variable, which we call Z. If Z is greater than 2.33, the time series is non-random with a confidence of 99%. And the way that works is that we're looking at this distribution. So the number of runs, like if you have more than 20 instances of something, like you roll a die 20 times or more, then the expectation is that the random data will fit a normal distribution, and whatever you have, you can center it on 0 and give it a standard deviation of 1. That's producing the Z value. So the Z value is indicating how many standard deviations you are away from the mean of the random process. And in your case, if you have very few runs, but the random chance would normally expect lots and lots of flip-flops, so lots of runs, then that small number is going to be indicating a very strong deviation. So I feel like I'm getting very technical, but backing up a minute, you're just trying to say, do I have data that's like very noisy, or do I have data that's very patterned? Okay, but you don't want to just look at it and decide. You want a specific test, and you can do this in Excel very quickly, as you will be doing in a homework. So let me show you just another example. Let's say I have this discharge data here, and it's just ordered by day. And then I calculated the median. The median of those points, I'm sorry this is to the side, but it's 10.73 basically. And for those of you, you can chide me now because I've got all the sig figs here that are not sig figs. So, but I'm going to say it right. It's like median of 10.73, and this is just the raw data, so you can't fault me for that. So then I say, okay, is this value greater than 10.73? Yes. So I give it a 1. So this is easy for Excel to do. I get all the 1s, then 0s, 1, 0, and so on. Now A and B are the A and B are the number of 1s, right? The number of 1s and 0s I have. R is the number of 1s. So here's a run of 1s. Here's a run of 0s. So that's 1, 2, 3, 4, 5, 6. So there's 6 runs. And then I calculate RU and sigma according to the equations here. Very simple, A and B. Just do the math. And I find these values. Z equals basically -5. Well, that means I'm 5 times the mean, or away from the mean expectation by 5 standard deviations. Well, the odds of that happening are very low. Like if you were to just roll dice randomly, it would be very, very improbable to get this result. Like heads, tails, heads, tails. Like getting this distribution is very unlikely, and therefore we have a very high confidence, well above the 95% level. Like actually, like 99.9999% confidence level that this is non-random. And I love this test. I do this test all the time. Like whenever I have a grad student, I say, do you know if your data is random or ordered? Because that's the most basic thing you can ask yourself in science. Okay, so there's a couple more, even more sophisticated analyses to look at predictability. The first is one we've talked about quite a bit with tides. It's harmonic analysis. So if you can find that your data is made up of sine functions, those are very predictable. So here's an analysis from the Susquehanna River in 1995 in gray and 1996 in black. And we have 2 axes for the 2 data sets. And frequency is the number of times per day. Obviously, for discharge, these are going to be much less than 1. So, 0.3 would mean that it's going to happen once every 3 days, 0.1 once every 10 days. And you can see there are some very strong amplitude events here where there are cycles in Susquehanna River flow during these 2 years. And they do repeat in these 2 years. This is an even more sophisticated analysis. I've already talked to you before about Fourier analysis, and I've shown you this evolutive Fourier analysis, but now instead of doing it for tides and winds, I'm doing it for discharge. So you can calculate the spectrum of the frequencies for your data for each individual year, and you can then see from year to year what changes, and you can see there's not a whole lot taking place except for what this one peak is, which is the annual cycle, essentially. And then the last metric from the natural flow regime is flow rate of change, or flashiness. And I just want to give you a heads up because on the exam, I asked students a question about, something like, well, what is the slope of the rising limb? And, the rising limb is this part of the curve, right? So starting from 0, as rain turns into runoff, the flow increases until you reach the peak. That's called the rising limb. And the slope of the rising limb is an indicator of the rate of change. Just as the slope of the falling limb, the slope of this line or curve here, would be another measure of the rate of change. And so one student wrote, the slope of the rising limb is the slope and velocity of which a student's arm is raised to ask for the answer. And right now, my slope is at 90 degrees. So unfortunately, the student didn't know, but it's important to understand that flashiness is an important aspect of a natural flow regime. Of course, there's the flash floods that I showed in the Part 1 video podcast for this chapter, but doesn't have to be that extreme. If you're a fish and you're out on the floodplain, it's springtime, you're eating some food, and then all of a sudden, boom, the flow drops and it's gone and you're sucking air on some grass, then you're done. So it doesn't have to be, it's, during as a function of timing of the year and not just what flow you're at, but just how quickly the flow changes can have very strong ecological ramifications. The last thing is that now you've got these elements. So let's say that you have an altered flow regime, like the river has been regulated, it's been channelized, people have knocked down the trees, they've built the urban area and the lowlands with bridges. Maybe there's something you can do to put the flow regime back. So in the same way, like from a wetlands restoration perspective, I talked about the idea of going back to the way it was. Well, an E-flow regime is one in which you're creating an E is for environmental. So environmental flows, and we're trying to design a flow regime that obviously we don't have all the water to put back the way it was before, but try to get some of the essential parts of the flow regime back in place. So if this red line represents the original flow regime maybe, and then the blue here represents the regulated flow with a dam, maybe the goal is to release some spikes like these maroon colors, and to do certain things, release to flush the sediments. Like that's the biggest flow that you're going to release artificially. So you have to have a dam to do an E-flow, right? Or some kind of structure. Maybe you do some other flows to release or maintain habitat or aid migratory flows or fish or whatever it is. So this is just a way of like taking the natural flow regime, characterizing what are the indicators of alteration to that hydrological regime using the analyses I've talked about, and then use this E-flow regime concept to conceptually put back processes. Now, it's very important to understand the way most people are using this is pure mimicry. They're just trying to mimic what was there before without actually knowing if doing this will recreate the real functionality that the river needs. But still, it's a very early time, and we shouldn't be too critical. It's just to try to illustrate to you the idea that we can use the natural flow regime concept not only to evaluate rivers, but to think about how we might restore them. Okay, so that's a very quick overview of the natural flow regime. There's a lot of papers that are out there and a lot of other information that I encourage you to look at if you're interested in this topic more.